the last class we talked about recurrent neural networks. It is a sophisticated version of the neural network where there is the neuron remembers its previous state, what its outputs were, whatever its activities, and recursively it remembers the entire past history, but recent history it remembers more, and past histories it remembers less and less. But it is a mechanism for modeling and recognizing sequential patterns, not just one pattern but a sequence of patterns. But it had some deficiencies, some shortcomings. We briefly talked about it there in the previous class. We will go through that again, and then we talk about a new variant of neural network called Lstm, long short term memory, where it is able to remember things that happened not only in the recent past but also in the distant part. We will see examples of where this becomes necessary, and that explains the popularity of the Lstm. This is a famous quote which says, "Before you speak, let your words pass through 3 gates." Is it true? Only then let it go. Is it necessary to talk? And is it kind? So, before you speak, think of these questions, and only if your thought passes through these 3 gates, let you speak out. That is the old proverb. So, here we see the word gate. Gate does control the information flow. An example of a gate is the main gate of our institute. If a student comes with a student pass, the security guard let them go through as it is, no change. If a visitor comes in a Ola or Uber cab, the cab driver has to get down, show his driving license and make an entry. If somebody comes just to have a dekho, they will say, "Sorry, not today, please come on open day." So the gates control the amount of information that is passing through. They can say yes, they can say no, they can say conditional yes or come with some modifications. So we will use this term gates today very well. Specifically, we will be talking about 3 types of gates. One gate is about forgetting the information that we have already stored in the past about the history. Forget gate. Update gate. Whatever knowledge that we have, we update certain part of the knowledge. Updation could be selective, just like our security gate. And based on the current information that we have, the information that we had in the past, and the new information that came at this particular time instant, what should be the output of my neuron? That's an output. So we will be talking about each of them one by one. Before we go through that, we will briefly go through the recurrent neural networks and see their shortcomings and shortcomings of RNN that Lstms are able to overcome. This is the block diagram of a recurrent neural network. There is a neuron A here. It receives an input x at time instant t. The output at the time instant t, h, not only depends upon the input but also depends upon the state of the cell at past time instances, which is h t minus 1 and h t minus 1 in turn depends upon h t minus 2 and so on, all the way from time t equal to 1 or t equal to 0. So this is there is a loop mechanism here. The state of the You can unroll this loop and see that a recurrent neural network is a series of same neuron. The advantage with this is that this kind of structure is that at time instant t, the output ht depends not only on the xt but the state of the cell at all previous time instance. So it has in principle infinite memory, infinite history. But there is some problem with it. It has difficulty in remembering information that it received long way. It is long-term memory. Let us take an example where a language model, we are talking about modeling text, English language, it is trying to predict the next word based on the previous words. Now, if you look at this particular, we have seen words up to here. The clouds are in the. The next word is easy to predict. Clouds are generally in the sky. So you can predict that this is the next word would be sky, even without bothering about what was spoken earlier, what were the previous sentences and so on. So the short-term memory is good enough, but sometimes that is not sufficient. We not only need to look at the most recent information, but also the past information, very past information. Suppose it's a paragraph where the first sentence is I grew up in India, and then there are several sentences, and maybe 9th sentence is I speak fluent. What should be the next word? This is 9th sentence, but the first sentence says that I grew up in India. We are, human beings are able to remember this information that was spoken 8 sentences earlier, and able to predict speaking is a language, and most likely language is Hindi because that is the language that is spoken by a large number of people in India. Human beings do this effortlessly, this long-term dependency, long-term memory, but recurrent neural networks have some difficulty in doing this particular job. So let us look at a standard recurrent neural network itself. A recurrent neural network takes input at time instant t, it takes an input called as xt. It also receives the output at time t minus 1, which goes in here, which comes here, and it goes through a time hyperbolic activation function, nonlinear activation function, and output at time instant t is generated. The same output is fed to the same neuron through self-loop mechanism for processing at the next time instant. So this is the unrolled version of the standard recurrent neural network. Let us see how this recurrent neural network gets trained. Yesterday we didn't talk about this, but let's briefly just go through that. The training is called error backpropagation, but this is through the time. Why? The output here depends on not only on the current input but also on the previous inputs and previous states. So the error has to backpropagate through time, not just through layers. To do the error backpropagation, the training involves 2 stages. One, input is given, the various processing takes place at neurons, and output comes out. So this is called the forward pass. So let us take a typical RNN unrolled version. Time flows like this. The input at time 0 is x0, input at time 1 is x1, and so on. The state of the neuron, what it remembers, is let's call it as S0, S1, S2, S3, and so on. So at time, let us consider the time instant 1. x1 comes in, the feature vector x1 is multiplied by a weight matrix U, and it passes through a sigmoidal function, and then the previous state of the cell that again could be a vector. It gets multiplied by the corresponding weight matrix W. So the input vector gets multiplied by weight matrix xt is multiplied by the corresponding weight matrix U, and that is added to the previous state at t minus 1 by the corresponding weight matrix W. These two are added, it passes through a, let's say, time hyperbolic function, and that becomes the current state. And this current state gets multiplied by another weight matrix V to generate the output y cap t. Y cap t comes here. The difference between the y cap t, that is the predicted output, and the target output, desired output, is the error at time instant t. Now this error has to be summed over all time instants to get the total error. So in the forward pass, the x vectors are fed in and the errors are calculated at various time instances. They are all summed up. That is the total error, maybe squared error, whatever function it is. And this error we want to propagate backwards so that we weights of various matrices U, W, V. Let us see how this error is back propagated. We have the same structure here. Okay. Now the error is there, and let us say we want to update the matrix W. Let me make a note here that this W is constant at all times. It doesn't change. The W or U or V is time independent till in one iteration of time. That means W here and W here, they are all same. There is no W subscript T. It is not time independent. My goal right now, let us say, is to update this weight matrix. So I take the total error and compute the partial differentiation of the total error with respect to weight matrix. And that since E is summation over the ET, this is equal to summation over time of the delta of the ET divided by delta W. If we compute delta ET by delta W at various time instances, then we can compute this. So let us compute one such term here for t is equal to 3. So we are interested in delta E3 by delta W. Delta E3 by delta W by chain rule can be written as delta E3 divided by delta y cap 3, the output here, and delta y cap 3 on delta S3. Delta y cap depends upon the S3, and delta S3 depends upon the W here. The S3 depends on the input at that time instant and the state of the neuron at the previous time instant. WS2 and UX3. W is here, U is here. And it passes through the time hyperbolic. Now S3 depends upon S2. That's the key idea. And S2 depends upon S1. S2 depends upon W again here, and in turn depends upon S1 and so on. So you see that the delta E by delta E3 by delta W depends upon various W's at various time instances and on the state of the neuron at various time instances. So I can write delta S3 by delta W. This expression S3 depends upon S2 and S1, which means that you need to sum such a term over dependence of S3 on Sk for all time instances, k equal to 3, 2, 1, 0 and so on. So this term delta S3 depends upon delta W can be broken up as delta S3 depending upon delta Sk, previous case, k less than 3, and delta Sk depending upon delta W. So you see here there are multiple derivatives getting multiplied and they are getting added here. So let's look at this expression again, that at time instant 3, if you look at the gradient of the error at time instant 3 with respect to the W partial derivative, that depends upon the dependence of the state of the neuron at the current time instant 3, this 3, with all the previous time instances, and the previous time instances in turn depend upon delta W. Now this term can be written as delta S3 by delta S3 minus 1, that is delta S2, and delta S2 divided by delta S2 minus 1, delta S2 minus 1, and so on. This term itself is a product of several such terms. So you see that the derivative of at one time instant with respect to W has lots of products here. Most of these derivatives are between 0 and 1 in most of the activation functions that we typically use. When you multiply numbers which are less than 1, if you multiply several numbers, the product will be much less than 1. This is at time instant 3, you saw 3 products here. At time instant 10, you will see 10 such products. At time instant 100, you will see 100 such products. So, the effect of the S1 on S100 will be almost negligible because of this product becomes less and less as time passes. So the long-term memory of the recurrent neural network is poor. The gradient values shrink exponentially. Why it is exponentially? Suppose these numbers are p, and so this will be p power 3. That's an exponential quantity. P is less than 1. Gradient contributions from faraway steps become 0. If I am at S100, the contribution of S90 will be little bit, contribution of S10 will be very small, almost negligible. Therefore, recurrent neural networks have difficulty correlating long distance dependency. What is the long distance dependency? My first sentence said that I grew up in India, and the 10th sentence, or 9th sentence said that I speak fluent dash. So there may be 100 words in between, it is not able to remember this context. So that problem is called vanishing gradient problem. Sometimes, depending upon the activation function and the errors, the gradient can become greater than 1. This number could become greater than 1. Very large, exponentially grow up. So that problem is called gradient explosion problem. The standard or the vanilla of the recurrent neural network is unable to control this kind of problem, vanishing gradient problem or exploding problem. The long short-term memory, Lstm, came up to solve this kind of problem. It has a built-in mechanism to have the recent information to be stored and also relevant information of the very past, long past to be stored. So we need to determine what is relevance, what should we remember from the long past, what should we forget, and what should we update. These are done by gates that we talked about. The gates are called forget gate. Some information becomes useless after some time, so forget it. Information comes at time instant t. Not all information may be useful. A part of the information will be useful to update it. So even the input go through an input gate. Similarly, the output of the neuron also go through an output layer. It is not necessary to output all the information that it knows at the given correct time instant. Only part of the information has to go through. So the output of the neuron also has to go through a gate, this operating gate here. So there are 4 interacting layers. They are all connected to each other, therefore they are interacting layers. And this graph, bipolar, it shows these 4 types of gates in a compact manner. That is the current state of the neuron what information that it stores is also another. So we will go through each of these gates one by one. This was introduced in 1997, so 2 decades ago. Let us look at each of these gates. I want us to have a look at what is the need for different types of gates by looking at an example. The first stuff that one talks about is the state of the cell, Ct. Ct at time instant t minus 1 is there, and it gets modified by doing various kinds of operations, and the state of the cell, which has some information, is fed into the next time instance. So what are the things that this cell state need to remember, or could remember, or would be useful? Let's look at that. Let us take the example of translation from English language to Hindi language. It is translation from text to text. English written in Roman text to Hindi written in Devanagari text. So I am going to show the inputs here in the English language, and we want to guess what could be the translation in Hindi language. Okay. Let us say Arun went. So what is the corresponding Hindi translation? He went. Gaya. Okay? I am just going to write Gaya. Arun Gaya. Bharti went, another human being. What do you write? Bharti Gayi. Okay? Why? Because it is a person. Here, went and went, exactly same. The verb is gender neutral in English. In Hindi, verb ending, morphology of the word, that depends upon the gender of the person. Therefore, whenever a noun comes, it is good to remember the gender of the person when we are talking about the Hindi language. So the cell state, what it remembers would be, first it has to identify the noun, and part of speech is essential for every word. So you need to remember the part of speech for every word, and this is a noun, but its gender also you remember because that is necessary. Now let us say the English sentence is both went. Dono gaye. So the verb changed with respect to the plural or singular. So this information that there were 2 people earlier and both went or they went, you need to remember that plurality also. So the information that you remember based on the past sentences could be what are the parts of speech of the each word, and what is their gender, and what is the plurality, singularity. These things matter when you come to the Hindi language. Now let us look at this second sentence, another sentence. Arun is good, one sentence. He went. He is a pronoun. So what does it refer to? It refers to the person Arun. You need to connect up these two. The current noun is Arun, the person. Therefore this pronoun refers to this Arun. So you need to remember the current person. So that information has to be stored here. Let us look at the another sentence. Arun is a good boy. Anil is also good. He went. What does this he refers to? Most likely to the Anil rather than Arun. When Arun is a good boy was there, the noun is stored, noun of the current cell is Arun. When the sentence ended here and a new sentence started and a new noun came into picture. So we need to forget the old noun and replace it by the new noun. So we need a forgetting capability to forget information and update this information, and depending upon that, he will map on to Anil. We see the need for remembering things, selectively